Okay guys, this is part 2 of our discussion around quasi-linear utility functions and their demand. In this video, I'm going to discuss the nature and existence of our corner solutions when we have quasi-linearity. And just to remind you, in part 1, I was careful to think about the behavior of our marginal utility, and we found in example 1 that the marginal utility of x was asymptotic to the vertical axes. And so the marginal utility of the first unit of consumption of x was like mathematically infinite. The marginal utility of x, for example, number 2, in contrast, crossed our marginal utility axes at 1. The marginal utility for x in both cases was diminishing though, and the marginal utility for y in both cases was constant. We also saw that the indifference curves for example 1, they terminated at the vertical axes, and we saw that they became infinitely steep as they approached their intercept. In example 2, in contrast, the indifference curves crossed past the y-axis. Now, I also tried to be careful when I described that characteristic feature of interior solutions when we have quasi-linear utility, that there is no income effect on x, that this is really true once we already have an interior solution, or we might say if we are already consuming positive amounts of each good. And this all brings us back to our topic for this video, which is our corner solutions. And I'm just going to motivate things visually to start with. So I have here drawings of our indifference curves for both of our examples. And I've used dotted lines for areas where x or y are negative because we can't consume a negative amount of x or y. But mathematically, our indifference curves may extend to these regions. So let's consider the possibility of a corner solution then when our consumer consumes 0 of good x, so they only consume good y. And actually, this can only occur in example number 2 if the price of good x is relatively expensive enough. So the slope of our budget constraint, recall, is the negative of the price of x over the price of y. So if the price of x is really, really large relative to the price of y, then we're going to get a very steep budget constraint. So I'm drawing the budget constraint in blue here. So maybe something like this. And hopefully you can see the point of our tangency between our indifference curves and our budget constraint. It's actually going to lead to a negative x value like that. But of course, in real life, we can't consume a negative amount of a good. And so actually, in this case, it will be the consumer's best option to consume 0 amount of good x and spend all of their income on good y. That is to say, the highest indifference curve that they can reach, given their budget constraint, will be at the corner. So maybe like this. So you can see that budget constraint in blue. Given that budget constraint, our optimum then will be consuming on an indifference curve like this right at the corner. So x is equal to 0. We're going to spend all our money on consuming y. Now, it is also worth noting that this solution is characterized by the slope of our budget constraint being steeper than the slope of our indifference curve at that y-axis. Now, note also that there is still no income effect here. So if we increased income, this would not change this result. It would just shift everything up. Increasing income would not change the slope of our budget constraint or our indifference curve, so we would still get a tangency at negative x. Now, in our first example, this corner solution will not occur since, as I discussed before, our indifference curves get infinitely steep as they approach the y-axis. So even if the price of x was like really, really, really expensive, there's always going to be an interior solution where x is consumed in some positive amount. And we saw that with our MRS before, we saw that it wasn't defined at x is equal to 0. So the slope, which is the negative of our MRS, is also not defined at 0 and will approach negative infinity as x approaches 0. So we can take from these examples that we should not be looking for a corner solution where x is equal to 0 in every single case. It will depend on the equation, and we have to look for clues that this is happening. So we saw algebraically the behavior of the MRS, it was not defined where x is equal to 0. And also, if you remember, when we solved for our interior solution, for example 1, x star was like a squared thing. So that means that x star is always going to be positive, because if we square anything, that renders it positive. So we can never get a tangency value then where x comes out negative. In our second example, where that corner solution is possible, neither of these things were true. Our interior solution, x star, that we found, mathematically it can end up negative, which means that we could potentially find a tangency point where x is negative. And also our MRS was defined at 0. So these are the sorts of things you would be looking at when you get a question to try and figure out what's happening with the corner solutions. All right, let's think about our other corner solution where our consumer only consumes good x, so y is equal to 0. And actually the key here is that we can get this result in both examples if our income is not large enough. And this is actually the situation where we do have an income effect on x. So sometimes in the literature, we're told that there is no income effect on good x, but they'll qualify that with, if our income is already large enough or if we're already consuming positive amounts of both goods. So it's this sort of argument that they're getting at. So I'll show you this visually. Imagine we're in example 1, and this is the scenario. We have a budget constraint, and the slope of the budget constraint is equal to the slope of our indifference curve at that x value like this, and we get a nice internal solution. But let's reduce our income though. We're going to shift our budget constraint in, and you can see it's okay for a while. We still get points of tangency, but if income is too low, we don't have enough income to purchase that x that's associated with the tangency position given the slope of the budget constraint. And in fact, the tangency is going to occur when y is negative. So when our budget constraint is shifted in like this, we have very low income, we can't afford the x associated with the tangency point. Instead, in this case, the best that our consumer can do, given our budget constraint, is just to consume only x. So y is equal to 0. So it will be something like this. And you can see one of the features of this solution is that the budget constraint is flatter than our indifference curve at that corner. And so this is where we would get an income effect on x. At low levels of income, we're only going to be consuming x, will be at that corner. So, if we increase income, the consumption of x will increase. So we will get an income effect until our income is high enough to purchase that x star associated with the tangency point. And then after that, we won't have an income effect. And we can see this again in example number 2. This will be common to quasi-linear utility. If we had this budget constraint, so the x associated with the slope of the budget constraint is here. Well, if we reduce our income, eventually we're not going to have enough income to buy that much x. So we are going to have a corner solution. We would spend all of our income on x. We haven't got enough money to reach our interior solution. Now, the other really cool way to look at all this is to go back to our marginal utilities. I talked about it a little bit at this video, but also in part 1, and that gives us more clues as to what's happening. So recall, for example 1, our marginal utility of x looked like this. It was asymptotic to the vertical axes, and the marginal utility of y was just constant. And well, we can add to all of this the following perspective. Note that one way to think about our optimality condition for interior solutions. So when we set the marginal utility of x over the marginal utility of y equal to the price ratio, if we rearrange this, we get this condition that at the optimal, the marginal utility gained per dollar spent on x is equal to the marginal utility gained per dollar spent on y. And this is one way that some people talk about optimal consumption. The idea is that at the optimum, the amount of utility gained per dollar spent for both goods must be equal between both goods for that last marginal unit of each good purchased. And this is like a bang for your buck argument. At the optimum, the bang for your buck must be equal between the two goods for the last unit of each good consumed. And we can see about what happens if this fails. So for instance, if the marginal utility gained per dollar spent on x, if that was larger than the marginal utility gained per dollar spent on y, then we should be, if we can, consuming more x, because we're getting more bang for our buck from consuming x and less y if we're spending any money on y. And the converse is true as well. So if the marginal utility of y per dollar spent on y, if that's greater than the marginal utility that we get per dollar spent on x, we should just be spending more money on y if we possibly can and less on x if we possibly can. That would be the smarter thing to do. Now, further to this, if we go back to our diagrams, if we divide our marginal utility by our prices, this isn't going to change the shape of our graphs here in any meaningful way. It might make them a bit narrower or a bit wider, but it's not going to change that downward sloping kind of curved graph that we get for our marginal utility of x, or the constant line for our marginal utility of y. So we can replace the labels here without too much trouble, and then we can overlap our graphs, and this can help us understand our corner solutions and our interior solutions for our quasi-linear utility. So the idea is here, where in example number 1, for the first units of x consumed, you can see that marginal utility per dollar spent on x is greater than our marginal utility per dollar spent on y, since our marginal utility per dollar spent on y is just some linear, non-infinite straight line thing. So when we go from zero income to some small amounts of income, of course, we are only going to spend our money on x, because that marginal utility per dollar spent on x is greater than the marginal utility per dollar spent on y. As we consume more x, though, if we get more income and we consume more x, because of diminishing marginal utility, eventually we're going to get to a point where the marginal utility per dollar spent on each of the goods is equal. And that point is going to correspond to that x star tangency value. That will be that interior solution value of x. After which, if we get any more money, we're going to spend all of that additional money on y, because after that point, that marginal utility per dollar spent on y is greater than the marginal utility per dollar spent on x. So that's another perspective that we can take to understand what's happening, both with our corner solutions and our interior solutions as well. Now, for example, too, we have a very similar idea. We could get something like this, and this would be the same story. For low levels of income, we would definitely only buy x, because the marginal utility per dollar spent on x is going to be higher than the marginal utility per dollar spent on y. As we consume more x, though, eventually the marginal utility per dollar spent on x will be equal to the marginal utility per dollar spent on y, after which, if we consume any more x, that's actually lower. The marginal utility per dollar spent on x is lower than the marginal utility per dollar spent on y. So that's the same story as example 1, but note that because our marginal utility of x crossed that vertical axis, that means the marginal utility per dollar spent on x also crosses the axis. So we get this other possibility, which is here, where our marginal utility per dollar spent on y is always greater than our marginal utility per dollar spent on x. And so that corresponds to that other corner solution, right? That corner solution that wasn't possible in example 1, because in example 1 we had this asymptote, which means that the first marginal utility for the first unit of x consumed is like infinite, which a non-infinite thing can never be above, right? So that's kind of a nice way to understand the possibility or impossibilities of the corner solutions in these cases. So if I was in an exam or trying to figure out the question, I would definitely be looking at the marginal utilities, like just to start with, and just having a look at what they look like and their features. And this will help you to understand what's going on. That's what I think. That's my advice anyway. And we see also kind of nicely that the conditions that we imposed on the structure of our quasi-linear utility, right? We said that b of x had to have that positive first derivative and negative second derivative, and y had to enter in linearly. It's really those conditions that underlie the shapes of our marginal utility curves, and that really underlies the nature of the demand in this case. So that's really what is going on underneath everything. All right, let's get to our algebraic representation of demand. This is the last thing. So I've written here our interior solutions for example number 1. We've seen them before. We found those in part 1. Remember, for example 1, we're not going to get a solution where x is equal to 0, so no corner solution on the y-axis. But if our budget constraint looked like this does imply that the budget constraint will hit our indifference curve where that tangency value of y will be negative. And so if this occurs, the best we can do is set y is equal to 0 and spend all of our money on x. So algebraically, if tangency value of y is less than 0, x star is equal to our income divided by the price of x. That's spending all of our income on x, and y star is equal to 0. Now, since tangency y is equal to m over py minus py over 4 times px, I could write all of this down like this. We set x star is equal to py over 2px squared and y star equal to m over py minus py divided by 4px, unless m over py minus py over 4px is less than 0, in which case x star is equal to m over px and y star is equal to 0. So that's how I would write out my demand for example 1. Let's look at example 2. So our interior solutions, I have them down here. We have 2 possible corner solutions. One where our tangency value of x ends up to be negative, in which case we spend all of our money on y. And another possibility where y ends up negative, in which case we take the corner solution where y is equal to 0 and we spend all of our money on x. So algebraically then we have our interior solutions, but if the tangency value of x is less than 0, so if py over px minus 1 is less than 0, or to say this another way, if py divided by px is less than 1, then we spend all of our money on y, so y star is equal to m over py and x is equal to 0. And if tangency y is less than 0, so if m over py minus 1 plus px over py, if that's less than 0, then we spend all of our money on x. So we set y is equal to 0 and x is equal to m over px. All right, that's it. I hope that this helps. I will definitely, if I keep on doing the channel and keep on doing this, I'll probably redo all of it because it's a lot of content in part 1 and part 2. So if you're still here and you're listening to this, well done, because it's quite a lot. It's like 50 minutes or something, which is crazy. So there's a lot of stuff. I have to think about how I can communicate all of the different intricacies, and hopefully you got it. I really hope you got it. I hope I didn't make any mistakes, and I hope it made sense. So I hope it helped. If it helped, please like and subscribe as usual. Thank you so much for watching my stuff. Have a great one, everyone.